All right. My name is Jonathan, as most of you know, and today I'm going to talk about cross-platform game development with libgdx. I realized I should rename the talk because I won't be talking so much about the cross-platform part of it, because libgdx does all of that for you. So yeah. However, what's going on? There we go. That's me. I'm born in. I was born in Kolmården, a small town about 20 kilometers northeast of Norrköping. This was the only aerial shot I could find of it. It's monkey cage. It's way over there. Yeah. I've been looking. I think this photo should be from '63 or '64, based on the buildings that are built at this time. Yeah, it's not as much green hills anymore. More buildings, way more buildings. Yeah, I grew up in a family with a lot of music and computers. My father is a church musician. My mother is a music teacher, and they're both very much involved within computers and technology. But they were pretty early adopters because of that. Mainly I encountered Linux quite early because my father needed it for writing music. Or huh? Louder. Yeah, Linux. I encountered Linux pretty early because my father used to write music in a software that was developed for Linux. So they were quite early adopters, and yeah, I had a lot of interests in technology and computers, more of an obsession really. I used to pick all my toys apart to understand how they work and all of that. At 9 I was introduced to HTML, I think 9 or 10. Thought it was so cool. Wasn't that interested, but it was cool, to see that you can manipulate the computer to do something that you want. I know. Then my teens is pretty much this. Video games, TV series, movies, and music. Was pretty much here also a lot of obsessions. I don't watch or read as many books as I should, but I love to read about them. Read all the lore. I haven't got through the Lord of the Rings yet, but I know all about it because I've read all of it on, on the internet. I got more and more interested in games, as I said. And I want to know more about how they are made, how to make video games. And that got me into programming. So when I went to the gymnasium, I studied some C++ and web development. Thought it was cool, thought it was hard, but pretty fun. I didn't quite get it at first. At the gymnasium, I was really tired of school, so I decided I wanted to do something else. So I went to a folkhögskola. Called Geijerskolan, where I sang and played guitar for 2 years. It's a really cool environment. A lot of creative people who love music, people who love video games. So there was, a lot of singing and playing and hanging out and taking 2 years off, basically, from everything else. It's really cool. After that, I was ready to study and go to the university. So I went to Örebro University, where I had applied twice before, but I chose not to go there. I got in, but yeah, I could always find pictures of me in my coveralls. I couldn't find any of me studying, so yeah. I studied video game technology and simulation, which basically is a computer engineering course, I should say, with less math. right off the bat, I knew this was something I want to do when I studied, because the first course actually was discrete mathematics, and that in tandem with some basic programming with Python, I think. Yeah, Python. And we sort of, during this course, I saw the connection between math and programming and computer science, and that made, I was quite good at math, but I found it pretty boring. I wasn't very good at programming, but I thought it was fun. But when we studied that course, and I saw the connection between the two, math became way more fun, and programming became way easier. I never got the degree. I got 4 points left. I will get them, I promise, one day. And our final thesis I did with a friend called Joel. Some of you met him. Some of you had tried to recruit him several times. It's a small game. The final thesis in itself wasn't on making a game. It was on dynamic lighting in a two-dimensional environment, really. So what we did, we created a simple game, just a shoot 'em up. You can find it on Google Play, by the way, if you want to play it.
Was it cool?
Yeah, it's cool.
What's the name?
Fung, it's called, which is another name of Phong, a lighting shading algorithm created by a Vietnamese guy, I think, in the 70s. Yeah, it was the algorithm we used to shade all the objects. If you can see, these pictures are quite not so good, but maybe we can see that the objects are lit up by the lasers and stuff, which is something that's not done much in 2D environments. So we wanted to do that, basically. And we also created a Python script to create normal maps in order to get the depth of every object. But I won't be getting much into detail about that now. So, about this talk. Didn't everybody start out like I did? I thought that everybody who studies knows programming, and I know a lot of you also like video games. Have you never thought about what video games are made? Have you ever tried? That was I thought basically everyone did. Well, cool. I know programming. I should try to make games. I know a couple. I remember the first couple of days when I talked about what I've done in the past, my final thesis. And there were a lot of people who reacted, "Wow, you can make games? I don't have no clue how to do that." And I think, well, programming, it shouldn't be that hard. So that's where this came from. I want to show you how easy it is. I will only go with the programming, no game design, no art, or how to make a good game, because, well, this is a tech talk, basically. And game design, I'm not too good with game design, really. I like the programming part, so that's what I'm gonna talk about. I want to show you how easy it is, basically. So, about libgdx. It's an open source framework written in Java. You write only in Java, and you can compile to desktop, Android, iOS, and HTML5 with just a click of a button or a command line. It's
What do you mean by desktop?
Desktop as a desktop application.
Windows.
Yeah. It's built on top of another framework called LWJGL, which stands for Lightweight Java Graphics Library. It is not an engine. This is a common misconception with most game frameworks. This is a framework, not an engine. Example of engines are these: Unity, Source, Unreal, Crytek, and idTech. And an engine is basically when you have the game ready and you just put in all the rules and the levels, the graphics, animations, and sounds, music, sure, I could show you one of these, but then you get more into game design and not so much programming. There is programming, of course, but the programming is more catered towards the game, the design of the game. So that's why I chose to show you libgdx, because it's pure programming. Also, let's talk about reinventing the wheel. You know, why it's been done 100 times. Why should you write it again? My view of it is that you should learn, or at least learn the basics of how a game works before you actually use these tools. You don't get straight into Angular or React when you do front-end development. First you learn how JavaScript works and how the DOM works and how to manipulate stuff with, well, I don't know, jQuery or something like that. And then you jump into some framework. Same thing about databases. You don't learn how to use Hibernate or Spring Data from the start. You learn SQL and how to make stuff with a database driver. So that's where I come from. That's my view of it. So we're gonna make Breakout. Have you played it? All of you have played Breakout. Yeah, you can Google you can go do a Google image search for Breakout, and you can play Breakout in Google. Try it. Do you know who originally developed Breakout?
Tim.
Yeah.
Am I that old?
Yes, you are. It was actually Steve Jobs and Steve Wozniak. Steve Jobs worked at Atari in the early 70s, and he did. And at the time, games, you know, there were Pong machines and really basic arcade machines, and they were all made with discrete logic, just chips to put on. You program with chips, no microprocessors or something like that. Steve Jobs didn't know too much about that, but somehow he got designed to make this game, and he called his friend Steve Wozniak, who helped him out basically. Yeah. So we start by creating the game. It comes with a utility, small little Java utility for creating a project, where you just choose the platforms you want to deploy to. You choose some libraries. And then you just open the project and let it run in your favorite IDE or straight command line if that's your thing. And this is what the tool looks like. You just put your name in, what you want to call the base package, the base class. You also need the Android SDK. Even though you're not going to deploy to Android, you need the Android SDK because it sort of uses the app lifecycle of Android, even though you're compiling to desktop or HTML5. And then some extensions or plugins, some extra libraries. I choose not to use any of them, just a basic libudx setup. And then you open it in your IDE. I open it in IntelliJ here. So if you see, here we get a couple of Gradle modules. We get the core, which is a base game, and then we have desktop and Android. In those we have those are just one class projects that are basically just launchers of those. So if you want to run on Android, you just compile the Android module and you're done. It's pretty basic. It also creates you a base. It creates a base class. I will get into further detail what all these are, what's happening here. Yeah. So when I created that, you get this. Pretty basic, just draws an image on the screen. So what we need to do next is to define the world. We need to identify all the different stuff in the world that we need to create different classes of for objects. So, yeah, no, you could see it. What objects, what different types of entities do we have in a Breakout game? Bricks?
Ball.
The ball, and
the platform at the bottom.
yeah, the paddle.
It's movable.
The paddle, right. So, we have the ball. The ball has a texture, a size, and a position. We have the paddle, which also has texture, a size, and a position. And the block, same thing. Texture, do I need to clarify? Texture is just is a bitmap. It's an image, basically. It's called, yeah. So we do some refactoring and we make a base class called entity and some inheritance between those. So after that, we draw them to the screen. In the render method, I'm going to show this soon. Draw the entities using the sprite batch. I will explain. This must be done 60 times per second, or the libgdx we try to do this 60 times per second, give or take. And that's all you need to know. Now you know how to draw something on the screen. Now you just manipulate the values of these entities and you're done, right? So yeah, I'm gonna. No.
Yeah.
But really, that's the hard part, getting something drawn onto the screen. The rest of it you can just Google your way through, and it's really simple. But I'm gonna show you a couple of other neat things. So let's see here. Yeah, right. You saw on the base class we had a create method that was overridden. Here it's basically a constructor. It's called when the game is booting up. And here let's see here. We set up the paddle. We created some methods for creating these different objects. I forgot to mention, but we have, I created some constants which defines the width and the height of the different objects. And we load the texture using this object. This is an internal image. It just stores the bitmap locally. We set up the blocks. I could have just made a CSV file or a JSON file and load it in and parse that, but I think it's fun to write an algorithm to space the different things out. So that's what I did. You don't need to focus too much on this. This is just me having fun. Then,
but what you're doing there is actually just putting it
evenly spaced.
pixel by pixel.
No.
Is it actually like sprites or?
It's like no. It's not like sprites in that
but
manner.
you don't need like crash detection for each one of them, right?
Yeah, we're gonna get that. We're gonna get to that. Yeah, I just put in these objects evenly spaced between each node, and then I added to a big list which I call entities. All these objects. And then in the render method, we loop through all the entities and we draw them to the screen using the sprite batch. That's called batch here. The batch is basically an OpenGL wrapper for 2D graphics. You don't need to learn any OpenGL or stuff like that, low level. You basically just take the batch and you tell it to draw this texture at that position, at that size. And then you're done. It's drawn to the screen. And as I said, the render method, it's called 60 times per second. And it's has to be drawn every time, every one of these calls. You can't just, like in web development, you draw something onto a page and it stays there. Here you have to actually draw it every frame, or else it would just disappear. So, yeah, I'm gonna show you what we get. Can we? Oh, this is what we got, right? Yeah. Now, input, movement, and delta time. Now we're gonna get into some more hard stuff. Input is really, really simple. You just get the position of the mouse and set the position of the paddle accordingly. It's that simple. So here in the render method, the render also acts as an update method. Everything you need to do every cycle, you need to do from this method. And here I created a method called update paddle. And in here we just set the paddle's X position to the mouse X position. And we're done. It's really simple.
Question.
Yeah.
Who calls render?
The framework does.
Okay.
Yeah.
Won't the pedal go off screen?
No, actually, I'm going to show you, but it all captures the position within the screen. It does not outside the screen. Movement is a bit tricky. We need some more attributes for the ball. We need the speed of the ball. and we need the angle that it's going to travel at. So the speed is basically the number of pixels we're going to travel per second. And the angle is a vector with two float values, describing how much of the total speed is going to travel along the y-axis and along the x-axis. Simple as that. The values and those floats are between -1 and +1. That's all. So to describe this a bit simpler, we have the ball, and we have a speed of 300. We have dx and dy. That's the angle. It's basically radians, you can call them. We want to move it half of the speed in the x direction and half of the speed in the y direction. So we move every second, we move it along the x-axis 150 pixels and the y 150.
The speed is 300 pixels per second.
Yeah. So the total x and y, if you, yeah. So here in ball, we just we add those parameters, and then we're gonna need to go and then before we're gonna do any do any movement, we need to talk about delta time. Delta time is a value that describes the number of pixels, the number of how much time has passed since the last draw call, since the last time we called that render method, how much time has passed. So it's basically just a multiplier of a second. That's usually 1/1. It should be way less than that. It should be a 60th of a second, if optimally. If it's more than 1, then you got problems. You need to optimize your code basically, because then it has taken a whole second to draw something on the screen last time. So we use delta time to figure out how much we should move the ball. And it's pretty simple. We know that we're going to move the ball, say 300 pixels per second. We have a multiplier of a second that tells us how much time has passed since the last draw call. So we just multiply the speed with the delta time, and we get how much we should travel that 60th of a second. And yeah, and we also add in the factor of the angle. Just multiply that together, and we get the number of pixels along the x-axis, and the same thing for the y-axis. So here we have update ball. I added some logic, so the ball X is attached to the paddle in the beginning, and when I press space, it flies away. If it's not attached to the paddle, we update the ball, and in the ball class, I've added an update where we take in the delta time, and we simply add to the x and y position the angle times the speed times the delta time. And there we go. Is that clear? I need to further... No? Let's see. So, here's what we get.
Can you just repeat that the last delta time part?
Yeah, sure. Delta time. Delta time is provided by the framework, and this basically just keeps track of how much time has passed since the last. Yeah, so it's just a fraction of a second, basically.
Since the last.
Draw call. Since last time we draw something on the screen. If we would just every second move the 300 pixels, it will. We need to interpolate, so we basically just move the ball a little per draw call, you know. So yeah.
So why do we do update where we get delta time?
Where we did get delta time?
No, why do we do that?
Why?
As
This is a bit confusing. It's just if the ball is attached to the paddle. It's just some extra logic that you don't need to care about at the moment. But in the beginning, it's, we press space and the ball flies away, basically. Yeah. And then we get the delta time. Do I make any more sense? Yeah. So yeah. Let's see, where's the cursor? There. We have movement of the paddle on the ball, and we shoot away the ball, and it goes. Oh. Yeah. Wall collisions. Now we need to when the ball hits a wall or the ceiling, we need to reflect the ball's angle around the normal of the wall. That's a bit too complicated. We don't need to do all that math actually. All the edges are vertical or horizontal. There's never anything between, so we can simplify these equations. So if the ball hits a vertical wall, we set the direction of x to the additive inverse of x. The additive inverse is basically if 0.5, the additive inverse is minus 0.5, and the other way around. If it's minus 0.5, it's 0.5. So we just add or remove a minus, basically. So, and if we hit our horizontal wall, we set the direction in y direction. Same way. So yeah, to further illustrate this, yeah, the ball hits the wall. It's traveling along the x-axis. It's 0.5, 150 pixels. If it hits, we want to reflect it perpendicular to the wall, not perpendicular. Yeah, we want to reflect the direction basically. So we wanted to travel along the other and the opposite direction with the same speed. Basically, what is one we want to do. So we put a minus in front of that. So now we travel minus 150 pixels per second. So here's the code for that. Up here I have the update for the ball, and then we check collisions with the wall. We basically just check where does the screen ends and starts and ends. And we flip it around, just multiply it by -1, those directions. So here's what we get. Oh, I got some problems. Right, yeah. It works good enough. And as you can see, it bounces on the floor. It shouldn't do that, but just for debugging purposes. Add as many sheets as you want to your game. Just remember to remove them before you deploy. Have you heard of the Konami code?
Yes.
It's a combination of keys you put on certain Konami games on the Nintendo Entertainment System, which gave you a bunch of lives, and that was just for debugging purposes in the beginning, and they forgot to remove it, and then it's legacy, so now every game has to have that.
Also websites.
Yeah, true.
I added one to a previous company. If you would do it on a website, you get into a space game.
So, collision with blocks and paddles. To determine whether the ball collides with the paddle on the blocks, we use Minkowski addition or AABB collision. I'm not going to go into detail how that works, but it's pretty simple if you think about it. We get the combined height and width of the two, so we basically take the height divided by 2 and sum it up with the half of the height of the other, basically. And we measure the distances between their origins. If the distance between those origins are larger than their combined height or width, then it doesn't collide. So if you just work with the y direction, we measure the combined size, which is the half of these two together. If that's equal or less than the distance between their origins, then we have a collection. And we put that together with the x direction and we get a collision. That makes myself clear. Is it? No? So here we do that. Let's see, we take their combined width and height. We get the centers of these two. We measure the distance between those and we check the, we need to use the absolute value also. If it's equal or less than the combined width, we have a collision. So then we need to loop through all the entities and check the collision if they collide with the ball. Bounce the ball with the additive inverse, remove the block, if there is a block. We don't want to remove the paddle. So here we are. Yeah. Here we check, and here we, as I said, we loop through them all, and then when we check the collisions, we also check if they hit the left side, the right side, the top, or the bottom to reflect it accordingly, the ball. I'm not gonna go into detail how that little logic works, mainly because I don't remember. I just I've written this from memory and try to remember, but yeah, I ain't got that much time, so I'm not gonna go more into that. We reflect the ball. If it's a block, we remove it from the big entity list. I used instance of. I know I shouldn't, but yeah. So. Way.
Nice.
Oh. There we go. Yeah, it is. It's really a feature. So, what if there are more moving entities? Then we need to, if we need to check, basically, let's say we have a physical world that we have a lot of different objects. We need to collide together and check if they're. Then we basically need to loop through all the entities in a nested loop. So we loop through all the entities once, and for every cycle we loop through all the other entities. This can become quite costly, so we need to do some optimizations. I'm not gonna. Now this is quite simple game. It's not very resource intensive. But for example, what you could do in a 2D environment, you just shop the world up in a grid, and you assign all the entities to their grid. And every time you need to check collision on some moving object, you basically just check the objects around that in the grids around it, basically. Stuff like that you can do. You can do even more. If you check the direction it's going, you can only check what's ahead of it, and yeah, check if it collides. Yeah, and one thing about game development, if you ever get into it, you're gonna realize how powerful a computer is, really. When you do web development, for example, you don't really get that. But when you delve into all the math and stuff, you can make the computer do 60 times per second. It's quite amazing. You really, you won't get into that. So after some cleanup and some optimizations, this is what I've got. Bam! So I've added score, I've added lives.
Can you also, like, I always, when I played it, I had the feeling that I could, like, alter That went through your pedal.
Yeah.
That I could like change the direction by the way I would like hit it.
No, I haven't done it. I thought about
Was that true, or is this just
yeah, it's some games.
Arcanoid, for instance, does that.
Yeah. You can one common thing people used to do is it would bounce in a different angle, but depending on where on the paddle it hit. So if you don't know, it would bounce that way. So and it's quite simple. You just measure the distance to the center that the ball hits, and you, some cosine and sinus stuff. It's quite simple, but I choose not to get into that. Yeah.
So what if you wanted to do a curve trajectory?
Huh?
Curve trajectory.
Oh, well, then we get to more complicated stuff. There's basically, if you use Bezier curves, for example, it's the same stuff. You just interpolate it using the delta time. Some basic math, basically. But I won't delve into that much deeper. So, I showed the results. In conclusion, define the world and draw it to the screen. Move the objects using delta time and an angle vector, and then Google. It's that simple. Really, this is, I think, not more than 300 lines of code, not even that, maybe 150, I think. It's if you just use that concept of delta time and the angle vector, the rest of there's tons of resources on the internet because everyone has done it. It's really easy to get started. So yeah, that's that. Thank you.
Thank you.
Have any questions? Yeah.
Do you have it on GitHub?
Yeah. No, I put it on our private Bitbucket. I'm gonna open it up and share it. Yeah.
Risk för att en dum fråga nu då. In English, sorry. The 60-second stuff you were talking about,
Yeah.
is that FPS?
Yeah. Exactly. Yeah. And if
I'm impressed.
For my own peace of mind mostly, but the speed and using the angle, speed would differ, right? If you have like a straight line upwards, it would go 300 pixels.
Yeah.
But when it's 45 degrees, it will only move like 220.
45 degrees, it should be 150 per.
150 and 150, but the distance traveled wouldn't be at 300.
Yeah,
It's
the
20, something like that.
it's this.
Yeah.
Yeah, exactly.
Okay.
Yeah.
So just to make sure that I remember.
Yeah.
When you compile to HTML, what does it look like? Is it a canvas or is it JavaScript?
It uses WebGL, and I don't actually know exactly how it works, but I think it's a canvas. Yeah, it should be.
Another question. Was this libgdx? How
Yeah.
old is that?
I don't know really. I want to say about 6 or 7 years, something like that.
It reminded me a lot of XNA.
Yeah. It's based around the same concepts. Yeah,
Exactly.
right.
Basically that, but in Java and for
Yeah.
the platform.
Yeah, and XNA is discontinued.
Yeah. There's that.
And it's in C#, so.
Cool.
Yeah, right. Good.
Thank you so much.
Thank you.